Hey everybody, this is Larry. This is me going Q4 of the weekly time test for 18 sorted GCD pairs queries. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about this one. So this one was very tricky for me. I spent about an hour on this I took a break to solve Q3, but yeah, this was just very difficult for me. I think there are a couple of things you have to kind of have really good understanding of. One is kind of GCD, and the other is just primes and all the number theory stuff. I mean, maybe you don't have to be like super good at the number theory, but that's just the part of it. And playing around with the properties of what a GCD really means. Honestly, there are definitely a couple of ways you can think about doing this problem, but the way that I end up doing, and I'm not really happy about this, honestly, that Leetcode requires so much pre-processing, at least in Python, to make it work. But yeah, I think there is a lot of. I'm trying to explain it in a way such that how do you come up with, like, for me, as you know, hopefully as you know, in these videos I don't just explain the solution because honestly I don't find that interesting, because everyone else is already doing it, right? So when I'm trying, or like you watch read the discuss forum or whatever, anyone can look at the code and pretend that they understand and then just read it to you, right? So what I try to do is figure out like how, not just necessarily for you, maybe a little bit for you, but also even just for myself, if I see this problem again, how would I be able to attack this problem? What are things that I'm thinking of, right? The first thing to realize, of course, just some basic things to get it out of the way. This is a hard problem, and what it means by this hard is that n is 10 to the 5th, which means that you can't do anything n square, obviously, hopefully. You can't even, I don't even think you could store it, even if you can, but like in terms of memory limited, exceeded. Yeah. And then the second thing is to just notice that actually the range of the numbers are not that big. It's 50,000, right? So even though you have 10 to the 5th numbers, actually you can already immediately reduce it to 50,000 numbers, which is half of it. Because these are the number of distinct numbers, and they're the same numbers. You can do some math on it. It's not a big deal. And then another thing is realizing that we have a lot of queries, right? So we have a lot of queries. Each of these queries, they would have to be able to be answered in either all of one time or all of log n time at the worst, because anything slower and each query will just time out, right? So that's another thing. Yeah, and then of course the other thing is that you can't even store all the possible n's because that's just too many, right? I think I said that already. Or n squared, sorry. Yeah, and for each query you have to figure that out. And because we have these constraints, my natural inclination is to think about binary search for the queries, because honestly, these are just the constraints, and if you're required to be log n, it's very rare that it's not binary, or at least at this level it's not binary search. Maybe there's some like crazy complex algorithm at some point, but yeah. And the way that you think about binary search is that you just ask, okay, to get the x number, you ask, okay, if I have a 2, what is its position, right? If I figure that out, then I know that if it's before, then we know that we need a smaller number. If it's bigger, then we need to know it's a later number, and so forth, right? So that kind of binary search, I'm not going to go over in detail because this is a Q4. This is a very hard problem. I think that kind of binary search is actually comes up enough times on Leetcode that I'm not going to go over it. My apologies. You have to practice on your own time. Yeah, and the way that I think about it is that, okay, well, we have 50,000 numbers. What does that mean? There are two ideas that I had here, right? And one is that, spoiler alert. One is that given 50,000, right, how many prime factors are there, right? Well, it turns out that 2 to the 16 is like 65k, right? So that means that 50,000 has at most 16 prime divisors, right? Not necessarily unique, but every number will have at most 2 to 16 or 16 prime divisors, which means that most numbers don't have that many. Most numbers don't have that many divisors, right? So that's basically the idea. That's one idea. The second idea is the more naive one, right? And here we can maybe do something like get all possibilities from the prime divisors, right? And it's not quite, in the worst case it's 2 to the 16, but it's not quite as easy as that, right? Because it has to be unique, so it's not a binary in and out kind of thing. And what I mean by that is if you have something like 2 times 2 times 2 times 5 times 5 or something like this, right? You don't have to repeat, you don't have to repeat, 2 times 2, like as a divisor. So this is your number, which I think is 2000, right? So you don't have to repeat checking something like this. Like this is a divisor. This is another divisor, but it's not a unique divisor because because it uses different 2's, but it's not the same, right? So anyway, my point is that 2 to the 16 is an upper bound, but probably you can get a lot less on most practical numbers. The reason why I say that is because I think for this particular problem, almost every second, every operation counts. So you might have to be more precise about it. And then the other way is the more naive way, which is to count up to the square root, right? So and this is a very standard thing of like, okay, check every number up to the square root to see if it's a divisor and so forth. And that, of course, is just for 50,000. It's going to be square root of 50,000, which is like 223 or something, which is, 50,000 times 223 is like 10 million, which is on the cusp of okay, but I know that we're doing cheap operations, so maybe it'll be fine. So that's really my thought process. But it still took me a while to convince this, right? But okay. Another part that I think about is that, okay, remember that in this problem, we don't want the greatest divisors, we want the greatest common divisors, right? So this is the part that I struggle with a bit during the contest. I'm just going to bring up the whiteboard, right? And what I mean by that is that, okay, well, let's say we have the number 6. Oh, we're in gray today. I don't know what color this is. So, let's say we have the number 6 and we have 3 numbers in the thing that is divided by it, right? Okay, well, actually, let me just actually use some real numbers. Hang on. So let's say we have, go back to black. 6, 10, 12, 24, 20, right? Okay, I forgot to sort. Okay, so then now, how many numbers are divisible by 6? Let's start over. They're all divisible by 2, so there's 5 numbers divisible by 2. The 3, there's at least 3, right? And then 4, there's 1 number divisible by 2. I forget 20. 5 is going to be 2. 6 is going to be 3, and so forth. Right? That's it for now. And then the idea here is that okay. Then now, what is the greatest common denominator where it is you go to exactly 3? So that's the tricky thing, right? Like how many, because because for example 6 and 12 are both divisible by 3, but it is not the greatest common divisor, right? That would be 6. So the tricky thing that I had struggled with for a while is basically this, is that I go, okay, well, if there are 3 numbers that are divisible by 3 and 3 numbers that are divisible by 6, then there's 0 numbers that are only divisible by 3, right? That's kind of right, but not quite precisely yet. Because, for example, let's say we added a number 3, right? So then now this is a 4. And we go, okay, well, there's only one number, right? That is 3. But that's not quite precisely right? Because the idea that I was struggling during contest was that I have this idea of inclusion-exclusion, right? Because, for example, if, okay, I have 3, I look at this, and I subtract out the 6, but, you know, what if, and here, actually 12 and 24 has a 12, right? So there are actually 2 numbers that are divisible by 12. What do I do here? Do I subtract it from 3? And then subtract it from 2? And then so forth? And the idea here is actually some kind of, not for this problem, but the idea is inclusion-exclusion principle, right? Where, okay, we want to calculate the numbers that are divisible by 3 by removing the numbers that are divisible by 6, but also adding back in the numbers that are bigger than 6, but are divisible by 6, right? So I struggled with that for a bit until I figured out how to do the dynamic programming, which is what we have for this one. And yeah, that's basically the idea or the trick of the problem. Is this sort of dynamic programming. So let's go over the code. It's actually not that bad, but it's, I don't know, I feel like this particular dynamic programming took me a while to kind of realize, because I was trying to get around the needing to use inclusion-exclusion just because I didn't know how to do it. But yeah, okay, so this part just gets all the divisors, and as we said, I did the max times the square root of max kind of way, which is what we have here. We go to the max times the square root, and then we just basically have C, which is a list of divisors for that number. As I said, this is going to be max times square root of max times. But we only do this once for all the test cases, which is maybe why we're able to get away with it. Okay, and then now, yeah, we have a little max for the max of the current set of numbers for the current inputs. D for the number of frequency. We just basically do a frequency table for nums. And then F is, well, actually I have here, right? So F of C is the number of numbers that C divides, right, in the input. So given these input, F of C is the number of things that divides it. And yeah, we just do it very naively with the divisors, right? We just go, okay, for each divisor, we just increment it by that number of X. I mean, we already did this, so it's fine, right? And this is the DP part, which is that, okay, but we start at the biggest number, right? And we go, okay, well, so count sub X is equal to the number of inputs that input pairs that has X as the GCD, right? And the way that I do this is by counting it backwards, because basically if and this part is actually critical by counting it from bigger numbers down, because that means that when you get to the current number, it means that all the bigger numbers are processed, and also it means that whatever left over from all the numbers that are bigger numbers that are processed will be that this is the biggest one, right? So here we start with just the number of pairs with this number as any divisor. So the number of pairs with X as the divisor, and of course this is just n choose 2, which is the number of pairs, right? And then now for each multiple, we subtract the number of pairs, right? So which is the key thing that took a while, right? For each multiple of X, we remove that number of pairs from X. yeah, and that's pretty much it, really. This is the way so that we do it so that we don't double count. And the reason why we don't double count is because we're summing over all the multiples, and each of the multiples themselves already subtract from their multiples, right? So in that way, like if you kind of draw it all out, it makes sense, right? Because basically, and this is the idea that I kind of struggle with. Let me bring back the drawing board in a second. The contest with the visualization is that basically, for example, let's say you have a timeline, right? Yeah, let me draw it a little bit better. You have a timeline. It's not that much better, right? So let's say this is count of x, and then here we want to subtract from every multiple of x, right? But every multiple already subtract from their multiple, right? So for example, here maybe the multiple of that would be like here. So then this already subtracted from here. So then we don't worry about this getting double counted because this number already does not include any of the previous cells. So that is the idea. And because you can build on that, then every number will be unique coming forward. So that's, I mean, it is an idea and a technique that comes up once in a while. I think I've probably done this like 2 or 3 times over my life. So it's not that often, at least for me, because I haven't recently solved that many code forces / math heavy math contest, but yeah, but that's really the idea. But that said, as soon as I realized this, I knew it would be fast enough. You know, this doesn't look that easy, but to figure out the complexity. But if you kind of look at it backwards and just to count the loops, if not the order, then you have n plus n over 2, because for 2 you skip every 2, right? Plus n over 3 plus n over 4 plus n over 5 ... which should be you go to n log n or something, right? Or n log n maybe, but either way log n is a good upper bound, and that's really the idea for this complexity. So I knew that this would be at least fast enough, and this n is not the size of the input n, so sorry, it is actually n mx for this case, which is the number that we go up to. Okay, so then now we have all these numbers. So then now we have count sub x is equal to the number of input pairs that have x as the GCD. What will we do with it, right? Well, we call it that we want to, for each query, we want to get the next, we want to count how many numbers are smaller, or how many GCD numbers are smaller than it, right? So, of course, it'll be too expensive to sum it up all to, for example, for a Q, it's too expensive to kind of just like keep on going one at a time. So what you can do is just do a prefix sum and then binary search. And that's really pretty much it, because once you binary search, and again, I'm not going to go with the binary search for this problem because this comes up a lot on Leetcode and just want to keep it a little bit short and simple. But yeah, there's actually another way to do it now that I think about it, but I did it with binary search and it worked. So yeah, because binary search allows you to get, after you do the prefix sum will give you, I think you don't need the 0, so it's like off by 1 or something. That's why I have to do a -1 here. But after you remove but prefix sub I is equal to the sum of count from 0 to I, right? So that means that, yeah, which is another way of saying the number prefix of I is equal to the number of pairs that has I as the GCD or less. I or less, maybe I or fewer, as the GCD. So that's basically the prefix, and then now that leads you to be able to bisect it. So that's one way to do it. Another way to do it is actually noting that the queries are not really live, right? So you can actually rearrange these to process them in order with the prefix, so that you can yeah, so then as you process the prefix, you know what answers are on the queries that you can answer with the index. So you could do it that way, and that way you can actually get rid of the of the queue itself. But not really, because you have to still, because there you sort the queues and here you sort the n, right? So you get, either way is quite fine, depending on how easy you feel like you're doing it, right? So what is the complexity here? There's a lot of, like, based on the number, the biggest number, so it's a little bit wonky. I usually use D for the number of digits because it's kind of like the range. So for the number of digits, this is, well, maybe the number of digits is kind of wrong too, because then it's going to be exponential. Even though that is the size of the input, but yeah, this is going to be mx times square root of mx, as I say. This is mx log mx. This is linear time. Oh, sorry, this is linear time. This is linear-ish with the number of divisors, and the divisors are, I think, at most like on the order of log n, but I could be wrong on that one. It's something like that though. And this is linear. This is n log q log n, and yeah, or not even q log n, q log mx. So okay, let me write it all out. So okay, this is O of n. This is O of mx, log mx maybe, give or take. This is O of mx time. Oh, sorry, space, but O of mx log mx time. This is O of mx time and space, and this is O of q times log mx time, and O of q space, of course. And that's pretty much it. I mean, the actual complexity is just summing them all up. So let me give you my my body of the code, not my body, but also let me give you the square root one. I actually made a silly mistake because I guess the examples are two small numbers, but I actually forgot about the I divided by j. I feel so dumb for getting it out part wrong. So that's how I got the one wrong answer. But yeah, this is for getting the divisors, and this is the rest of the code for everything else. That's all I have for this one. Let me know what you think. Thanks for watching. And yeah, as to how I solved this one, I just kind of honestly, for every part of the way, you could watch me solve it live. Every part of the way, I just thought, okay, I think once I got this recurrence, I was like, okay, what do I need to do from the other stuff? And that's basically how I did it from here. Yeah. Because I was like, okay, well here, then I need to count, and the counts I need to count some of the divisors, and the divisors, well, we did the divisors, and then after that I'm like, oh wait, then I need the prefix sum because I need to binary search on the sums, right? So that's pretty much it. A lot of things going on here, like I said. I don't think it's very weird that I need to do this square root divisor strategy and do the CIF calculation strategy, which is the mx log mx1 at the same time, and then on top of that you have to do a prefix sum and a binary search. So pretty tricky problem, pretty tricksy. That's all I have for this one though. Let me know what you think. Thanks for watching, and yeah, you can watch me solve it live during the contest next. Q3, no one got, oh, people got Q4, so I'm going to try to do that one first. Why not? Or maybe just people doing it backwards. Okay. So n is big. You've got it already. Is it ChatGPT? GCD. Is it a prefix something? For each number, how do we do? Still no one got that one yet, so I don't know. I don't know that I know this one though, it's too mathy. But maybe there's a notepad time. Alright, so that's it for prime factorizations. Right, so then 2 square, you have a 2 and you have a 1. What does that mean? That means that this is just for each number. I try to figure out how big it is. 5. If you have like X, how do I know this is the GCD? If I have say 6 and 10. Five times 10, what is that? 50,000. Is it like an inclusion exclusion thing? What is the 2 times 2 to the 12? Nope. So it's like 2 to the 16. And one person got it. Well, it doesn't. At least it doesn't look like people actually got it. So maybe I should look at Q2 or Q3. Let's take a look at this form anyway. And nodes. What is this grid? Oh, all nodes from 0 to 1. Okay. 2 nodes should be an adjacent cell if there's only an edge between them. Okay, so 0, 1, 0, 2. Is that the only way? Probably not. There's at least 4 rotations and 8 of them if we count symmetry, so at least for a 2x2 grid. Oh, oops. People keep on telling me this one. They don't even tell us what the grid size is. But there's always an answer. Because this is always possible, I guess. I mean, there's just, even the 0 is the 3 possible ways for 1, 4, and 5. This also seems impossible for me to do, honestly. Well, Q got Q2 very quickly too. I don't know which one's more doable. I think maybe Q4 still. I just have to figure out the maths. Well, the n doesn't matter because they're dupes. So, which is actually a little bit odd. Well, I mean, it matters with the dupes. So let's say we have, okay, n log n. So let's say we have 6. Is 6 to GCD if how many numbers? Okay, 50,000. If we do a sieve, how would the sieve work? Every 2? Okay, so we have a 6 and a 10, and then we have I think it's going to be 2. 2, we have 2 numbers here. At 6 we have 1, and we have 1. But how do we know that it is a GCD and not just a denominator? Like, what do we have? Oh, even 6 and 12. If we have 2, we have, okay, well. And for each number, doing 2 to the 16 is too expensive. Oops. Okay, let's say we have 1, the smallest number 1. Get rid of it. Okay, now we have 2, 4, 4. So just divide and conquer. So now the smallest number is 2. Go through all of them. That's n squared if you're sloppy. Okay, if we sort the numbers, the smallest number has to be GCD to all the other numbers bigger than it. That's not true. It could be 1. All the numbers bigger than it. That one still looks harder, at least for ChatGPT. People got Q2 really fast too. Alright, well, there we go. Cannot be n squared. Is that a try? No. Maybe I just don't know it. I need a new page. I don't even need a new page, but. Can we pre-process the queries at all? Do the queries matter? I guess there's 50,000 unique numbers only. I don't even have a good idea on Q3 either. And it seems impossible with only 2 people getting it. Let me reread the poem, maybe I read it wrong. No, it seems like I did not read it wrong. How many ones are there? Do binary search on the Let's say we were safe. Whatever. Twos are not, they're not the GCD, they're just the divisor, right? In that case. Maybe this is an early ghost ignite. I tried to do this one first, but I guess I just don't know how to do it. I have half an hour. Can I do it in half an hour? I hope so. If you keep on messaging me. Yeah, we can redo it. And I spent so much time on this one too. Okay, for example, how do I okay, let's say we do every divisors, right? So if we have every divisor, can we do it? Is the square root of 50,000? Is this one of those like 223? What is that times 5? Is that fast enough? 10 million? We could pre-process it. Is that enough memory? Well, okay, let's say we have the divisors, then what? this one on memory? Yeah, screw it. Okay, fine. One second to pre-process. That's not so bad. Silly that we need to do it though, but okay. So then now we have I even need to do this explicitly? I can just do it like a... And then now prefix sum, and then now we have... Okay, so then now... Oops, that's not reuse stuff. Well, I have 20 minutes. Let's see if I could finish it. Okay, then now for here. So this is a divisor, right? And that is the number count. Okay. And then now, what's C divides? I'm trying to think through this. Okay, so then now, do we just do like right? There's the number of pairs, right? So choose 2. Is it faster if I just do this? Oh, whatever, let's just do the math. Is it plus or minus? So do we choose 2 is 6? No, do we choose 2 is 3, so 3 times 2 minus 1. So it's minus, right? I'm so bad at this. Okay. Okay, so that double counts all the pairs that we already have. So then now we do another sieve. I'll make this slightly bigger. Oh, and this should be this max. Doesn't have to be the other max. I'm getting confused. Okay, so then now okay. Does this make any sense at all? Oh, the F should be okay. Oops. 17 minutes. This takes a while. It's because of this. Silly Larry. This is too slow though, if this is the case. Is it here? Or oh, this is fast-ish. Oh, because x could be 0, you idiot. Yeah. Okay. Okay, so that means that that's not quite right? Oh, actually that is. Well, 2 has 1. Oh no, I'm looking at the wrong one. Let's look at this. Okay, so that's good. 7 1s and 2 2s, is that right? Definitely not right. This one do I do? Oh. 7 1s, 2 2s, and is that too many? We only have 12 pairs, right? 4 times 3. Now we have 6 pairs, right? So that means something is wrong. Let's say we don't have this yet. I thought it was something like that, but okay, so we 1 4, okay, we're Gucci. We get to 2, we have 3. We have 3 numbers. But we also want to subtract the number of pairs that have higher, so there should be 2. This seems right. So this is 2. And then 7 is because we have 4 numbers, so then 3, 4, 3 is 12. That is 12. 4, 3 is 6, right? So this should be 6. Am I just doing this wrong? Do I reuse something somewhere? Why is this so bad? Why is this giving me 5 numbers? Dot keys. Do I double count 1? 2 is 1, 2, 1, 3, 1, 4. Okay, 4, 2. Oh, we do count, double count once. Oh, because of this thing. If I is okay, so then this is 6. Is that right? 3, 1, 2, 2. I mean, it's just fast enough. That's the thing. I mean, then now we have prefix sum, and then we could binary search, right? All right, so we should be able to get this, but apparently a lot of people got it. Okay. Yeah, I mean, okay, fine. I mean, I don't need to print prefix sum to check. Am I that incompetent these days? Okay, so we want the first, so if it's 0, we want the first number such that oops. Nope, that's not the syntax. Something like this. I may be off by 1 though. It says 4, 2, 1, 1. This isn't even right. 1, 2, 2. This isn't even, so it's not bisect left. Okay, think about this for a second, Larry. You have time. Think it through. Okay, so you have, this is 0, oh, well, it's a little bit awkward anyway. But with the prefix 0, it can never be 0 anyway, right? So basically we want the 0th element. Oh, it's the 0th element, not the 0th number. No, we do prefix, that should be good, right? So we have 0 numbers that are less than it, so it's bisect, right, maybe? Okay, I mean, this is maybe fine. I just have to subtract it by 1 for the extra 0. Extra 0 didn't make sense anyway. We probably didn't need that 0. 1, 2, 2, 4, 2, 1, 1, 2, 2. Alright, I'm not super confident just because of off by 1, but let's YOLO this. Okay, I knew I was going to have it off by 1. Maybe I should think about it. 6, 3, output 1, 6. The answer should be 3. Why? Do I have an off by? I have an off by 1 somewhere else actually. On. Do I? Why would it be on 1? This isn't right. Okay, so I start at 6. 6 should be 0 count. Oh no, this is prefix sum, so that's fine. So we have 1 at 2 or 1. Count. Okay, well this count is just wrong. So I guess that's that. Silly typo somewhere probably. It's either that or something wrong with this part. Okay, so you have this thing. Does that even make sense? So we have 2 with 1s. No, because it doesn't have 3. Why doesn't it have 3? Or 4, 3? Alright, we have 8 minutes. Hopefully I get it. Okay. 1, 3, right? One, 3. We add 1. We add 3. Well, the 6 is wrong. How do I get 6 wrong? I get 6 wrong because I am an idiot that doesn't know how to do divisor. Yeah, okay. Larry, you silly goose. Okay. It's been too long, maybe. Too long being an idiot. Alright, still print out stuff. Alright, let's print out a little bit less. This still looks good. Alright, let's YOLO. I mean, that was way wrong. Okay. Wow, I'm surprised that it passed. Let's take a look at the submission time. Because I'm not... Okay, 1.8 seconds is fine. That's a very hard thing to gamble on, though. But, I mean, I did okay. I think more than 74 QA, though. Okay, I don't know. Maybe a lot of people did not super... Well, Q3 is hard. I don't know if Q4 is hard. It's just hard to tell. Honestly. I think it's just hard to figure out the complexity. I wasn't quite sure about the prefix. I mean, it's weird that you have to both use the CIF and the divisor thing all in once and have to do the math to make sure that it was okay. But, yeah, I think it's maybe the first time they have to use both, so I think that's a little bit tricky. Oh, 68 maybe. I mean, but 5 minutes penalty. Yeah, I was thinking along these lines for a while, but I just couldn't figure out how to. I wasn't able to prove it, honestly, a little bit. That yeah, I mean, I think this DP is important because I think the way that I was thinking about it initially was that I didn't know. That's why I was bringing up inclusion exclusion. Is because I thought that because when you remove something that's bigger, then now you have to bring it back in. But I guess if you just do a DP, then it's already factored in. So I think that's the part that I was missing for a while. Well, and this part, I suppose. But yeah, I mean, overall, not a terrible content. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, this video, everything between the contest. And stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.